I'm Prof and welcome to Chemistry Matters. And today we are going to be talking about the fundamentals of equilibrium. So, what do we mean by the term equilibrium? If you have watched some of the previous videos in this series, you'll have noticed me talking or using the word equilibrium, talking about it, but not really defining what it is. So it's probably an opportune moment to have a look at exactly what it is that we mean by equilibrium, okay? So in the video on phase diagrams, we talked about the fact that these lines on a phase diagram are equilibrium lines, okay? So what does that mean? It means that at any point, for example, along this line here, the equilibrium line between liquid water and water vapor, at any point on that line, the two phases are in equilibrium. In other words, we have both phases present at the same time in unchanging amounts, okay? The composition of the system is essentially constant along those equilibrium lines, okay? So, and again, that's true of any of the lines on this phase diagram of water. Here is your solid-liquid equilibrium line, for example, and again, at any point on that line, both ice and liquid water are in equilibrium with each other. So in other words, at particular values of P and T, you're going to have a certain equilibrium situation where the solid and the liquid are in equilibrium with each other, or indeed along this line here where the solid and the gas are in equilibrium with each other. So what does this all mean? What is this equilibrium thing? So first of all, how do we denote an equilibrium? Well, let's take ice in equilibrium with liquid water, and we would write this equilibrium like this, okay? We would say, okay, we have got ice here, solid water, and here the equilibrium symbol, okay? Sort of a double half-headed arrow, one going in the forward direction, the other going in the reverse direction for reasons that we'll see. And this is an equilibrium with liquid water, okay? Now, this equilibrium arrow implies that this reaction is going in both directions. And indeed, at equilibrium, it absolutely is, okay? So, for example, if we took a sample of ice and water, and we kept it at exactly 0.000 degrees, and we kept it at exactly atmospheric pressure, 1.013 by 10 to the 5 pascals, when we look at it, we would monitor that, and we would see that the system wouldn't change at all. The amounts of ice and water in the system would stay exactly the same. And it would look to us like nothing's happening, but in fact something is happening. And what is happening is that ice is melting, but water is freezing at the same time. And both of those processes are going on at the same rate. So ice is melting at the same rate that water is freezing. So to our eyes, nothing is actually happening. There's no overall change in the composition of the mixture. And that's essentially what we mean by equilibrium. So you have equilibrium where a forward reaction is occurring at the same rate as a reverse reaction. And that means you're at equilibrium, okay? So let's have a look at, now that was a phase change, let's have a look now at a chemical reaction, a classic chemical reaction, N2O4 gas in equilibrium with 2NO2 gas, okay? Now, so N2O4 is a gas, it's a colourless gas, and NO2 is a nice brown gas. And so we could think of doing an experiment where we take pure N2O4 in a flask and we just leave it to do its own thing. And we would start off with a colourless gas, and eventually, after time, we would see that there would be a brown colour starting to be formed in our flask. Likewise, we could start with pure NO2 gas, and we could put that in a flask, nice deep brown colour, and then leave it over time. You would see that brown colour start to get lighter and lighter and lighter. Now, depending on what side you start from, it doesn't matter, because your final reaction mixture is going to be exactly the same colour. You're going to have the same proportions of N2O4 and NO2 gas in your mixture, okay? So for example, if you started with 0.0350 mole of N2O4 in a litre, or if you started with 0.0700 mole of NO2, twice the number of moles of that, in a litre, it wouldn't matter which side you started on, because at the end, then what you're going to have is 0.0292 mole of N2O4 and 0.0116 mole of NO2. It doesn't matter which side of the equilibrium you start from. You start with pure this, or you start with pure this. You still get the same mixture after time, okay? You leave it until it goes to equilibrium and you get the same mixture there, okay? And so we can show this on a diagram like so, okay? So the red line here shows the concentration of N2O4 steadily decreasing until it comes to a stop and stops decreasing. The concentration of NO2 is shown here in blue, and it steadily increases and then stops changing. So after this point in time here, the concentrations of these two stop changing. And we say that we have come to equilibrium, okay? We've come to equilibrium. And the equilibrium concentration of those two are the same that I put down on the whiteboard just before. Now, a really important point about equilibrium, remember we wrote the equation N2O4 gas in equilibrium with 2NO2 gas. Let's look at the stoichiometry of this. Now this is, again, something that a lot of students have trouble with. If we took 1 mole of N2O4 and let it do its thing, we would not get 2 moles of NO2. But you might look at this and say, well, hang on, that's what the stoichiometry says. It says that 1 mole of N2O4 will react to give 2 moles of NO2. No, it doesn't. What it means is that for every mole of N2O4 that reacts, twice the number of moles of NO2 will be formed. And there's a difference in those two statements, okay? So we're not saying that this reaction goes to completion. 1 mole of N2O4 does not give 2 moles of NO2, but every mole of N2O4 that reacts forms twice the number of moles of NO2. But we go to equilibrium. We go to an equilibrium mixture of the two, okay? Now, how do we denote an equilibrium? Well, we can write a thing called an equilibrium constant, K. Now, there are 2 types of equilibrium constant. We're going to concentrate mostly on a thing called Kc. And Kc is when we talk about our composition of our reaction mixture in terms of concentrations, okay? And so for this particular equilibrium, our equilibrium constant is going to look like this. It's going to look like the concentration of NO2 squared divided by the concentration of N2O4, like that. And we would put a little equilibrium, E for equilibrium there, okay, although that's often left off because it is implied. This is our equilibrium constant expression. And not only does the equilibrium has an equilibrium constant expression, it also has a value, the equilibrium constant, and that, for this reaction, at 25 degrees is equal to 4.61 times 10 to the power of minus 3. So that's the value of the equilibrium constant. So what is that telling us about this equilibrium? Well, it's much less than 1. Okay, the value is much less than 1. Now, an equilibrium constant pretty much always is a quotient, like this, okay? We're doing a division here. if we have got a value much less than 1, that means that the top line is very much less than the bottom line, which means in terms of amounts of these two components at equilibrium, the product is going to be present in a smaller amount than the reactant, okay? At equilibrium, we're going to have less NO2 than we are N2O4, as shown by the value of our equilibrium constant being much less than 1, okay? So you're probably looking at this and saying, ooh, hell, where did he get this from? Where did this expression spring from? Well, we can write a general equilibrium constant expression for a general equilibrium. So here is our general equilibrium equation. A moles of A plus B moles of B in equilibrium with C moles of C plus D moles of D. Okay? If we've got that particular general equilibrium, then we can write Kc for this as being concentration of big C to the power of little c, concentration of big D to the power of little d, over concentration of big A to the little a, concentration of big B to the little b. And we can put little equilibrium e's there just to show that those are equilibrium values. So what do we got here? A general equilibrium constant expression. First up, products on the top line, reactants on the bottom line. So the concentration of your products on the top line, concentration of reactants on your bottom line. Everything raised to the power of its stoichiometry, okay, or the stoichiometric coefficient to give it its proper name. Little c, little d, little a, little b. Those are the numbers in your balanced chemical equation. So you raise the concentration of big C to the power of its stoichiometric coefficient, little c. Raise big D to the power of little d. Raise big A to the power of little a, etc., etc., etc. And that is your Kc expression. Now, of necessity, it's a simplified version of that particular expression, but we won't get too much into that. I will show you that if we're not using concentrations but we're using pressures, then we have a thing called Kp, P for pressure, and then the expression becomes a little bit more complicated, and you'll see why we sort of shy away from this. So this is the pressure of big C to the power of little c divided by P standard, the pressure of big D to the power of little d over P standard, all over, yes, it's getting complicated, the pressure of A to the power of little a over P standard, all to the power of C and to the power of D and to the power of A, and Pb to the power of B over P standard to the power of B. And yeah, that does look complicated, doesn't it? So I'm just giving you that so that you know what it is, so that you can say that you've at least seen it. But what we often find is that it's much, much easier to go with Kc because you don't have to divide through by P standard to the power of whatever, okay? So that is Kc and Kp. What does all of this mean? What's your take-home message for today, Alan, I hear you say, okay? The take-home message is that we can write an equilibrium constant expression. Let's call it Kc. And if Kc is very much greater than 1, then we are going to be on the side of products, because it means that the top line of your Kc expression is going to be big, bottom line is going to be small, Kc is going to be big. If Kc is very much less than 1, then at equilibrium we're going to be favouring reactants, okay? Because that's going to mean that the top line of your Kc expression is small, bottom line's big, therefore we're going to favour this. And if Kc, surprise, surprise, is approximately equal to 1, give or take a bit, then essentially you've got a 50-50 situation where you've got roughly, doesn't have to be exactly the same, but you've got roughly equal amounts of this and this at equilibrium. Okay? So, one other thing about equilibria that I will mention in passing, this will become very important later on. Just to finish this off, is that the only things that you put in equilibrium constant expressions are gases and species in solution. So, in other words, gases, bracket G, species in solution, bracket AQ, meaning aqueous. So we put these in, that's all good. We don't put in pure liquids or pure solids. They are the big no-no. They do not go into equilibrium constant expressions. Okay, as I say, we will talk about that in subsequent videos. Right, that's the basics. That's the basics, the fundamentals of equilibrium. That's enough for the day. So we will see you in the next video.